Recall that in the past few lectures, we have been talking about the vector potential for a magnetic field, which I denote by A r, such that curl of A is B. In particular, in the previous lecture, what we found is that A can be expressed as mu 0 over 4 pi integration over the volume, the current density J at r prime over r minus r prime over the volume. And we solved a couple of examples for different current distributions giving rise to A. In this lecture, I want to take one particular example that is similar to the example of a charged sphere or charged shell, similar to a charged shell, and I will take this vertical axis to be the z axis, with sigma, the surface charge density sigma theta, being equal to sigma naught cosine of theta. Recall that this gave us the electric field inside the shell as minus sigma 0 over 3 epsilon 0, a constant electric field, and outside it was like a dipolar field with a dipole moment P, whatever that comes out to be. Now, a similar situation occurs in magnetic field. If I take a sphere, so for a magnetic field, a similar situation occurs if I take a sphere, rather a shell, and have a surface current density k on it, which is k sin theta in the phi direction. Let me show this current here with red color. It is a current at everywhere, it is only on the surface, is flowing in the phi direction if I use the spherical polar coordinates. The current could arise out of charged shell rotating with certain angular speed, or as we will see later, also this is equivalent to a magnetized sphere. So, this is only on the surface. Therefore, if I were to ask how much is the current at a certain point passing through this line, then you recall that this length is going to be r d theta. So, the current through this small r d theta is going to be k sin theta times r d theta in the phi direction. In any case, I want to now calculate the vector potential for this. By definition, the vector potential A r will be equal to mu naught over 4 pi integration j r prime over r minus r prime d v prime. I could write j for this as j, since this is confined to the surface, will be k sin theta delta of r minus r, where r is the radius of the sphere, as you have already seen, in phi direction. And therefore, I will quickly change this integral to a surface integral and write this as A r equals mu naught over 4 pi integral k sin theta in phi direction, it should be sin theta prime in phi prime direction, divided by r minus vector r d s prime, where vector r denotes the vector on the surface. Right? Vector r denotes the vector on the surface. R is the point where I am calculating the vector potential, and k sin theta prime gives me the magnitude of the surface current, and phi prime is the phi unit vector prime is the direction of it, and we wish to calculate this. If I expand this, I am going to get A r equals mu naught over 4 pi, k comes out, inside I am left with sine of theta prime, phi prime I can write as minus sine phi prime in x direction plus cosine of phi prime in y direction divided by r minus vector r d s prime, where d s prime is now, let me show it again over this sphere. D s prime is the surface area over the sphere. This vector is r, and I am calculating the vector potential at some vector r. So, this becomes equal to mu naught k over 4 pi integration sin theta prime sin phi prime over r minus r d s prime in minus x direction plus mu naught k over 4 pi integration sin theta prime cosine phi prime over r minus r d s prime in y direction. Keep in mind that this vector capital R that I have written, right, vector R is nothing but R is fixed sin theta prime cosine phi prime in x direction plus R sin theta prime sin phi prime in y direction plus R cosine theta prime in z direction. Why I am writing this is because I want to emphasize that this R out here includes these theta prime and phi prime, the integration variables. Let us also write d s prime. What is d s prime? D s prime is r square sin theta prime d theta prime d phi prime. So, this because this is the integration over the spherical surface. All right. Now, you must be wondering how to calculate this integral. So, let me write this again and give you the answer first, because right now I want to focus on the vector potential, and in the next lecture I will tell you how to calculate these potentials using analogy with the electrostatics. So, right now what I have is I have A r equals mu naught k over 4 pi integration sin theta prime sin phi prime over r minus r, where this r capital R vector includes d s prime minus x. This r capital includes theta prime and phi prime, mu naught k over 4 pi integration sin theta prime cosine phi prime over r minus r d s prime in y direction. Let me quickly tell you what these integrals will be, and I will explain them in the next lecture. This integral sin theta prime sin phi prime over r minus capital R. Let me write to show explicitly that this capital R is a function of theta prime and phi prime. D s prime is equal to 4 pi by 3 r cubed over r square sin theta sin phi for r greater than r or greater than equal to r, where theta and phi correspond to r vector, and this is equal to 4 pi by 3 r sin theta sin phi for r less than r. You can see for small r equal to r, both of them match. Similarly, if I look at integration of sin theta prime cosine phi prime over r minus r, again I want to emphasize that capital R is a function of theta prime and phi prime, is equal to 4 pi by 3 r cubed over r square sin theta cosine of phi for r greater than or equal to r, and is equal to 4 pi by 3 r sin theta cosine of phi for r less than or equal to r. So, we have gotten these integrals for both sin theta prime sin phi prime and sin theta prime cosine phi prime, and therefore, my answer for A r is equal to mu naught k over 4 pi, then I have a 4 pi by 3 r cubed over r square sin theta sin phi in minus x direction plus mu naught k over 4 pi by 3 r cubed over r square sin theta cosine of phi in the y direction. This is for r greater than or equal to r. Let us simplify this. It will be mu naught k over 4 pi times 4 pi by 3 r cubed over r square sin theta I can take common, and this quantity sin phi minus x unit vector plus cosine phi y unit vector is nothing but phi vector unit vector. So, this is for r greater than or equal to r, and for the other limit I have mu naught k over 4 pi times 4 pi by 3 r sin theta sin phi in the minus x direction plus mu naught k over 4 pi times 4 pi by 3 r sin theta cosine phi in the y direction for r less than or equal to r, which again comes out to be equal to mu naught k upon 4 pi times 4 pi by 3 r sin theta, and again I can write this quantity in the green enclosure as phi unit vector for r less than or equal to r. So, in the final answer I have A r equals mu naught k over 3 r cubed over r square sin theta phi unit vector for r greater than equal to r, and is equal to mu naught k over 3 r sin theta phi for r less than r. This is my final answer for the vector potential. What about the magnetic field? The magnetic field B r is given as curl of A r. Notice that curl, and notice that A r has only phi component, and we are writing this whole thing in spherical polar coordinates. So, use the standard curl formula for calculating curl in spherical coordinates and that gives you the answer B of r is equal to mu naught k r cubed over 3 1 over r cubed 2 cosine theta r plus sin theta in theta direction for r greater than or equal to r, and this is equal to 2 mu naught k over 3 r in the z direction for r less than or equal to r. So, you see when I look at this sphere, a spherical shell that has current, surface current k going like k sin theta in phi direction, the field inside is constant. It is similar to electric field being constant if a shell had a surface charge density which was sigma naught cosine theta. What about outside? I will show you that the outside field is like the dipolar field. Like this. So, this is the kind of problem that we solved in electric field, and this is similar problem in the magnetic field, except that now it has a surface current density with sin theta dependence. Let me, before I finish this lecture, show you that outside field is really a magnetic dipole field. For that, let us write this B again. B r is mu naught k r cubed over 3 1 over r cubed 2 cosine theta r unit vector plus sin theta theta unit vector. Recall that magnetic field due to a magnetic moment m is equal to mu naught over 4 pi 3 m dot r unit vector minus m itself divided by r cubed. Let us take m in the z direction with magnitude m z, then I have B r, we use a different color, is equal to mu naught over 4 pi times 3 m dot r now would give me m cosine of theta is r unit vector minus m z unit vector I will decompose into theta and phi, which then gives me cosine theta in r direction minus sin theta in theta direction divided by r cubed. So, this gives me mu naught over 4 pi and I have 2 m cosine of theta r plus m sin of theta in theta direction divided by r cubed. You see, this has the same dependence on cosine theta and sin theta as the answer here. Let us compare terms. Let me take this m out and write it here, so that this factor enclosed in red is the same in both. So, what I am left with is, I will write it on the left hand side, mu naught m over 4 pi is equal to mu naught k r cubed over 3, or this implies that this sphere which carries a surface current of k has a magnetic moment of the magnitude m equals k times 4 pi by 3 r cubed. So, outside the magnetic field outside this sphere is like that produced by a point magnetic dipole with magnitude k 4 pi by 3 r cubed, and inside it is a constant field.